Hey there, and welcome. Today we're going to break down a fundamental law of physics. It's something that explains everything from your own reflection in the morning to how we can measure the exact distance to the moon. It's a principle that's so simple, but what we do with it, well, that's truly out of this world.
You've seen this before, right? A lake so perfectly still it looks like a sheet of glass mirroring the sky. But what's really going on here? How does light from those mountains and that sky bounce off the water so cleanly to create that image? Well, it all comes down to one single, elegant rule.
Okay, let's dive into this. Seriously, every single reflection you have ever seen, whether it's crystal clear or super blurry, is all governed by this one straightforward idea. Once you get this, everything else just clicks into place.
And here it is, the law of reflection. All it says is that the angle a ray of light bounces off a surface is exactly the same as the angle it came in at. The angle in equals the angle out. That's it. That one little equation really does explain it all.
Now, here's the key to really understanding this law. We don't measure those angles from the surface itself. No. Instead, we imagine a line sticking straight out from the surface at a perfect 90-degree angle, right where the light hits. We call that line the normal. Think of it like a tiny flagpole. Both the incoming and the outgoing angles are measured from that flagpole. And this is crucial, because it works no matter how the surface is tilted.
So hold on. If the same law applies to every single surface, why does a mirror give you a perfect image of yourself, while a piece of paper just looks, well, white? The secret isn't in the law. That never changes. The difference is in the texture of the surface itself, way down at a microscopic level.
And that brings us to the two big categories of reflection. First, you've got specular reflection. That's the fancy name for what happens on super smooth surfaces, like a mirror or that calm lake. It's organized, it's clean, and it produces an image. Then you have diffuse reflection. This is what happens on rough surfaces, like, say, this piece of paper or a wooden table. It scatters light in every possible direction, and that's actually why we can see things that aren't shiny. Light is bouncing off of them every which way for our eyes to catch.
And this brilliantly illustrates what we're talking about. See on the left? For specular reflection, all the parallel light rays come in together, they bounce off and they stay together, perfectly preserving the image. But look at the right. On a rough surface, even though each individual ray still follows the law of reflection perfectly, they all hit at different little angles, so they scatter in a total mess. The result? No clear image.
Here's a perfect real-world example to lock this in. That glazed pot on the left? It has an incredibly smooth surface, so you get those sharp, bright, mirror-like highlights. That is pure specular reflection. The unglazed pot next to it, though, has a rough, porous texture. Light hits it and scatters diffusely all over the place, which gives it that nice, even, matte look. It's the same law of physics at work, but with totally different results.
Let's move to and see how this builds. We know how it works on a flat surface, but this is where things get really fun. What happens when we take that mirror and we curve it? This is where reflections start to play tricks on our eyes. You know, you don't even need a fancy science lab to experiment with this. You've got the perfect tool sitting in your kitchen drawer right now. A regular old spoon is actually two different kinds of curved mirrors rolled into one. The inside part, the part that holds the soup, that's what we call a concave mirror.
Go ahead, try it. If you look into that concave, curvy inward side up close, it'll magnify your reflection, kind of like a makeup mirror. But as you pull it further away, poof, your face flips completely upside down. Now flip the spoon over. That's a convex mirror. It curves outward. This side will always give you a smaller, upright reflection, but it shows you a much wider view of the room around you, just like those security mirrors in a convenience store.
Okay, speaking of the weird things mirrors do, let's tackle the biggest mirror mystery of them all. You've wondered this, right? You raise your right hand, and your reflection raises its left hand. So the mirror obviously flips left and right. But why doesn't it flip you upside down? Why not up and down?
Well, the answer starts with a fantastic twist. The mirror isn't reversing left and right at all. The entire question we're asking is based on a false premise. It's a trick. So the crucial point is this. A mirror only does one thing. It reverses front and back. Think about it. When you look in a mirror, the tip of your nose is closest to the mirror and the reflection of your nose is closest to you. The back of your head is furthest away, and in the reflection, it's also the furthest away. The mirror has effectively taken the 3D you and turned you inside out along that front-to-back axis.
That left-right flip you think you see? That's not the mirror. That's your brain. Your brain sees this front-to-back reversed person and tries to make sense of it. It imagines a twin of you walked into the mirror world and turned around to face you. And in that mental rotation your brain performs, that's when left and right get swapped. The mirror itself is way simpler than that.
All right, so we've got the theory down. Now let's look at how this one simple law is at the absolute heart of some seriously advanced technology. Once you understand how to control reflection, you can do some incredible things, from talking across space to basically becoming invisible.
So meet the corner reflector. It's such a simple but brilliant idea. It's basically 3 flat mirrors all joined together at 90-degree angles, just like the inside corner of a cardboard box, and it has one incredible trick. Any light that goes in bounces back out on the exact same path it came from, no matter the angle.
And we use these things everywhere. They're the reason the little reflectors on your bike or on roadside signs shine so brightly when your car's headlights hit them. They're designed to send that light right back to the source. In this case, you, the driver. They're on boats to make them show up on radar. And most amazingly of all, they're on the moon. I'm not kidding. During the Apollo missions, astronauts left behind panels of these corner reflectors. Today, scientists from Earth can shoot a powerful laser beam at the moon, hit one of these panels, and because the light comes straight back, they can time the round trip of that light with unbelievable precision. This lets them measure the distance to the moon accurately to within a few centimeters. Just think about that. So that's how you make sure a signal bounces right back to where it came from. But what if you want to do the exact opposite? What if your life depends on not reflecting a signal back to its source? Well, then you build a stealth jet.
Stealth aircraft are basically a masterclass in manipulating the law of reflection. They're carefully designed to have almost no 90-degree angles, nothing that would act like a corner reflector. Instead, all of their surfaces are angled to take an incoming radar wave, which is just a form of light, remember, and bounce it away in some other direction, anywhere but back to the radar dish that sent it. So when you really get down to it, the law of reflection is all about looking into the past. It shows us the path a ray of light took to get to our eyes. It tells us where light has been. But that raises another question. What happens when light doesn't bounce off something, but passes through it, like when light goes from the air into water? What about where light is going? And that is a story for another explainer. Thanks for joining me.